Hi, my name is Michael Braverman and today I will present new ground freezing system which was developed and tested at Scotty Creek Research Station. We all know that thawing permafrost represents a real problem, especially in the region of sporadic and discontinuous permafrost, where it is thin enough to disappear literally in front of our eyes. But even in the high latitudes, any infrastructure built on it at some point in time will be affected by its thaw. There are several approaches how to mitigate this problem, but main tool for today which has highest efficiency is the thermosiphon. Thermosiphons allow to extract heat from the ground and release it to atmosphere, thus preventing permafrost from thaw. In North America, two-phase thermosiphon is the only type which is currently available on the market. Two-phase thermosiphon is a sealed thick pipe partly filled with liquid carbon dioxide under the high pressure. It operates during wintertime due to the temperature gradient between ground and air. Latent heat of vaporization makes this system very efficient. The design of this type of thermosiphon, which was introduced to the market in early 20th century, was not changed since then. As a disadvantage of this system is a high installation costs and generally it is not flexible in its applications. This is an example of two-phase thermosiphons which were installed at the roadway embankment at Chena Hot Springs Road in Fairbanks, Alaska. Our group designed and tested new type of thermosiphons. It excludes high-pressure operations, making it less expensive for installation and more flexible in its application. Two types of thermosiphons were developed, active and passive. Both of those types are filled with antifreeze, which flows inside vertical metal pipe under gravitational gradient, or as forced circulation. On the left side of this slide is active thermosiphon. The pump in the top of the thermosiphon creates constant flow of the fluid. The pump can be connected to the solar panel or any other power source. On the right side is the passive thermosiphon. The fluid circulation occurs due to the difference in density in the colder top and warmer bottom of the thermosiphon. Both systems were tested in peatlands not far from Fort Simpson, where permafrost affected at most by warming climate. Both systems were installed above existing permafrost, which was found at the depth of about 1.5 meters. Active layer in this region is about 0.5 meters, so our thermosiphons were installed in almost 1 meter of year-round unfrozen soil, which is peat, and it is about 80% of water and 20% of organic material. This is typical ground temperature profile for this site. With high amount of heat stored under active layer, only layer near the surface experiences negative temperatures in wintertime. As it is seen from this graph, the conditions for ground freezing system are most unfavorable. Here are the test results of both types of thermosiphons. Just two depths were chosen for this presentation, 0.9 meters, which is somewhere in the middle of unfrozen layer or tailing, and 1.5 meters, just above permafrost. As it is expected, performance of active thermosiphon was better compared to passive one. Nevertheless, from our point of view, minimum temperature reached of -7 degrees Celsius for passive thermosiphon can be considered as a success for the test. Briefly, advantages and disadvantages could be summarized as next. Active thermosiphon is highly efficient due to the forced circulation, but it requires maintenance. Passive thermosiphon doesn't require any maintenance, which makes it more attractive for remote site applications. But both systems have general drawback. Due to the high thermal conductivity of the metal pipe, there is a heat transfer through conduction in summer from above ground to underground part of the thermosiphon. So the same problem has the system which is currently on the market. Our research in Scotty Creek, which is not related to thermosiphons, showed that there is a year-round water flow through unfrozen layer or tailing between different water bodies, such as bogs and fens. As an experiment, it was decided to install our freezing system across one small channel, which connects Scarbog and Old Seismic Line. Our goal was to prevent water flow or heat and mass transfer from this bog into the seismic line. On the right picture, you can see actual field conditions where the thermosiphons were installed. And as you can see, it's lots of water. This is the temperature profile in the middle of the channel. Before thermosiphon installation, it was unfrozen all year round. After installation, it became frozen during wintertime. Also, we got significant reduction of summer temperatures. This is a representation of water level in the bog of interest. The yellow line is water level in the period of 2015 to 2016, and the blue one is for period of 2018 to 2020. As you can see, there is a consistent water level drop from November to May due to the flow of water through tailing into the seismic line. Before installation of the ground freezing system, blue line almost mirrors the yellow one, but in period of November 2019 till May 2020, after thermosiphons installation, there is no water flow out of the bog. It means we stop flow in the winter, but still see some flow in summertime. Worth paying attention that summer water level in 2020 is about 20 centimeters higher than in 2016, which can be due to the elevated bottom of the channel due to the permafrost recovery. And at the end, I would like to mention that we are still working on improvements of the developed system, such as the reduction of heat penetration in summertime through the skin of the thermosiphon. We are testing new system in the season of 2022, but at this point it's too early to talk about our results.